We good? All right, we're going to go ahead and start the review seminar. So the way that we plan to run this review seminar, this is more on Professor Shams' request than anything else. We're going to go over just go over a bunch of practice problems that we think will probably be relevant or you might encounter similar during your exam. Specifically, the points we're touching on, we just asked specifically from Professor Shams. So yeah, hopefully these are questions that, to our best guess, you might encounter during the exam. Some of these we took from the textbook. Some of these we modified from previous exam questions. It's sort of that size. We're going to start off with just some quick fire warm-up, just some true and false. So for each of these, I'll have a raise of hand for if you guys think it's true or false, and then I'll tell you the right answer. So first one, the law of large numbers implies that the sample mean for x approaches or converges in distribution to the actual mean as n approaches infinity. So you can check your notes. If you think it's true, raise your hand. If you think it's false, raise your hand. OK. Well, for this one, the answer is actually true. It is, oh, that's an erase. For this one, the answer is actually true. Reason being, specifically, it's the word implies. It's not states. If I had written the word states, this would 100% be false. Because if you recall from your notes, the law of large numbers implies that the sample mean approaches in probability or converges in probability to the true mean. However, if you remember correctly, convergence in probability does imply convergence in distribution. So the implication is there. It's not an equivalent relation. Does anyone have questions regarding that? No? OK. Number two, at least one maximum likelihood estimator will always exist, even if it's not necessarily unique. Hands up for true. Hands up for false. Yeah, it's false. All right. Number C. For some estimator of a general parameter theta, if we lower the variance of our estimator, we will decrease its bias. Hands up with true. Hands up with false. Yep, correct. That's false. Again, this kind of follows directly from the definition. If you remember what mean squared error is, it's specifically the variance of t minus the bias of t, or plus the bias of t, excuse me. The method of moments estimator for sigma squared in a normal distribution is unbiased. Hands up with true. Hands up with false. So the method of moments estimator for sigma squared, I believe, is unbiased. There's a proof in, I believe it's week 3 of your notes, saying that you can find the n-1 version, which you spend an entire week going over why it's unbiased. Oh, excuse me. Yeah. For part E, we prefer the following estimator over this one. Yes? Oh, these are the same. Excuse me. Let's do, this one should just be n. Yeah. There you go. We prefer the n-1 variant over the n variant as an estimator of sigma squared because the n variant becomes more biased as n approaches infinity. Raise your hand if true. Raise your hand if false. Yep, correct answer is false. If you're wondering why, I believe they show you that the variance of this specific estimator is equal to something like n-1 over n sigma squared. And then it's pretty clear to see that as this approaches infinity, this approaches 1. Wow, my handwriting is awful. OK. For F, the smallest confidence interval at a gamma of 95 confidence for any sampling distribution will contain its sample mean. Hands up with true. Hands up with false. Okay. Yep. That is right. I believe the correct answer is false. Yes. To find the confidence interval for the mean of a normal distribution, where the variance is unknown, we have to utilize, no worries. We have to utilize the t-distribution. Hands up with true. Hands up with false. I believe, yeah. So yeah, this is a trick question. It is the t-distribution, but it's the t-distribution with, or sorry, I should say n. It's the t-distribution with n minus 1 degrees of freedom. Now then, for any chi-squared, this is just a general k, so chi-squared with any general degrees of freedom k is symmetric on R. Hands up with true. Hands up with false. Yeah, this one's pretty clear. Just you could draw out the PDF for this, and it looks something like that. Yes.
In part G, since the sample size was not specified, do we always put the assuming n?
Yeah.
Or n plus 1 is true?
Yeah. If the sample size, well, sample size is needed for most of these calculators, especially like sample mean, sample standard deviation, all that kind of stuff. You need the n. And so it's normally just written arbitrarily as n. Even in future stats courses, you'll always see n as your sample size. So yeah. Final true false. As the level of significance increases, the chance we reject the true null hypothesis also increases. Hands up with true. Oh, sorry. Yes, you have a question? H. Sorry, no, that's false. That is my bad. All right, for I, level of significance increases. The chances that we reject a true null hypothesis also increases. Hands up with true. Hands up with false. So this one, I believe, is actually true. And it's true by definition because the level of significance, you recall in lecture, it's your type 1 error. And your type 1 error is specifically the probability that we reject our true null hypothesis H0. Or sorry, our hypothesis H0, given that H0 is true. So as this increases, quite literally, it increases the chance that we reject this true null hypothesis. So this one is actually true, and it's true by definition. So the level of significance is equal to the type 1 error, which is equal to that. And so by definition, this is actually true. Any questions?
Part B, can you give an example?
Part B? At least one will always exist. Oh, that's a good question. I think the easiest one to think about would be not every MLE is differentiable. I think it's one of the things gone over in your class. He says that not all of them are differentiable, and I can't think of one off the top of my head. Malhar, can you think of one where the MLE doesn't exist? Yeah. All I know is it's mentioned in your week 1 lecture notes. There's a singular line that says MLE doesn't always exist. And then for non-unique, you could just think of like uniform distribution. Uniform distribution has, MLE has like constant MLE everywhere. All right, so now we're going to move on to questions. The way we'll do these questions is I'll show them up on the screen for a little bit. I'll read them out. I'll give you maybe 3 minutes to work on them, and then I'll work through the solutions with you guys. So first question, we are given a population of normal distribution with unknown parameter mu and known standard deviation of sigma. We are interested in estimating the mean of our population, and so we draw a sample of 7 independent values. The independence here is very important. You'll need it for your calculation. And for the time being, consider these values to be unobserved. You draw the following 2 estimators. I want you to check whether or not these 2 estimators are biased. And then more of an intuition, which one would you prefer to use? So our first estimator is this very long linear combination. 0.4x1 plus 0.1x2, 0.7x3, 0.15x4, 0.35x5, 0.01x6, and 0.02x7, all times half. And then the second estimator, more simply, is x1 a good estimator, I guess? So yeah, I'll give you 3 minutes starting now. And if you have any questions, feel free to raise your hand during that time. One minute left. OK, it's about 3 minutes. If you're not done working, you're free to keep working. I'm going to start the solution, though. Hopefully, my handwriting is legible. If it's not, please let me know, and I'll try and clarify it. So recall first that the bias of some estimator t is equal to, we're estimating mu here, so I'll just specifically say that, is equal to the difference between the expectation of t and mu. And so t is unbiased if the expectation of t equals mu. That gives you a bias of 0. So we can check the bias here. The expectation of t1 is equal to, we put all of this in a big ol' expectation. So 0.4 x1 plus 0.1 x2, all the way up to, where are we? 0.2 x3 or x7. And then linearity of the expectation means that we can actually distribute the expectation all the way in. So that gives us 1/2 times 0.4 expectation of x1. Oh, handwriting's getting worse. Plus 0.1 expectation of x2. Plus all the way up to 0.2 expectation of x7. Now then, for each of these xi's, the expectation is already given because we know that these follow the normal distribution with some unknown parameter mu. But we know that whatever that unknown parameter is, we would expect the expectation of xi to be mu. So these are all, in fact, equal to mu. So therefore, this is equal to 1/2 of 0.4 mu plus 0.1 mu plus all the way up to 0.2 mu. If you add all of these decimals up, you actually get 2. So it becomes 1/2 times 2 mu equals mu. So therefore, T1 is unbiased. Now then, expectation of T2 for this question is way simpler. The expectation of T2 is just the expectation of x1, which is equal to mu. So actually, these are both completely unbiased. Anyone have any questions? Yes?
Can you explain the difference between using mu versus putting x bar instead?
Yes. So mu is our true parameter, right? It's, if you take the population, we don't know what mu is most of the time. So mu is representative of what the actual true parameter is. X bar is how we would estimate that. So the only way we would know what mu is mu is true mean, whereas x bar is our best guess. And that's what sort of central limit theorem tells you. It's what technically weak law of large numbers also tells you this, but it's saying that the more elements of our population we consider when we calculate x bar, the closer we get to the true mean. And if you think of mean sort of as like the traditional definition of, add everything up, divide by n, if you consider every single person in your population, like let's say you were doing a census report, if you somehow managed to get a meaningful data point from every single person in your population and you calculate that mean, that is your true mean, technically. But seeing as, how many people are in Canada, that's basically impossible. And so our best guess is we take some meaningfully large sample and x bar is our best guess of the true mean. Does that answer your question?
Yeah. So you couldn't use x bar in this question as well, or that's...
So you can't use x bar in this question because the expectation is, how do I put this? The expectation, by definition, you can't do for x1 because you would have to know every value x1 takes. But here, since we haven't actually given you the values for x1, then you can't find it. So what you're referring to, I guess, is x1 bar, right? Like for expectation of x1. Is that what you mean? Like, why can't we use this? It's because we don't know the values of x1. Because right now we say that we've drawn these 7 samples, but we don't know what they are. x1, or all of our sample elements, are random variables at the moment. And so technically this is the same, but it has to go over every single possible value that x1 takes. And if you look at every single value x1 takes, that is just your entire population. So here they are equivalent. Yeah. And then also, you need to get mu in there somewhere. And so you have to always assume that the expectation of x1 by definition is mu. Now, the second part of this, which estimator would you prefer to use? I think this is more fun as a show of hands. So hands up if you think you would use T1 as your estimator. Hands up if you think T2. Technically, they're both unbiased. So from this point, it looks like they're both good. But the next question will help you understand why not. Because even just looking at it intuitively, this is a super silly, like a very silly way of doing it. So part B, trying to zoom out, calculate the mean squared error of both estimators. And does this help our justification in part A? That justification being we as a majority seem to prefer. t1. So that's what we mean by that justification. Again, 3 minutes on the clock. You can go ahead and start. Meantime, I'll try and clean some of this up. About a minute left. All right, I'm going to start on the solution here. So the first thing that we'll need is that the MSE is equal to, or the MSE for some t is equal to the variance of t. Let's see here. I believe it's plus, yeah, plus the bias of t squared. So we already showed above that both t1 and t2 are unbiased. So that means that for t1 and t2, we don't have to think about this. It's just the variance of t. So all we have to do is calculate the variance of t1 and t2. The variance of t1, this one is, it's honestly an exercise in your calculator more than it is for you. If you think it took a long time on your calculator to do all this, don't worry. We chose 7 because it's just barely too big or barely too long for doing on your calculator. On your exam, you will probably run into 5 numbers rather than 7. So if you think you're barely out of time on this, don't worry. You're technically on pace. We just wanted this to be a little bit harder than what you might see during an exam. Did you have a question? Or no? Okay. But yeah, you'll be fine if you can barely get through this. Yeah.
I think there's a trick to calculating variance of t1.
Yes.
t1 minus u as some factor x1 minus mu plus some factor x2 minus mu, because we know that they add up to 1 mu. And we know that x1, x2, and x7 are independent. So if we are adding, when you multiply two x1 and x2 or x1 and x7, anything, the expectation will get 0 because you are looking at independent variables.
I understand what you're trying to say. I'm going to find it. You're trying to say something like the variance of t1 is equal to the expectation of t1 minus mu squared, right?
Yeah.
So what does t1 look, because we want this in terms of xi's, right? What does t1 look like when we expand it out? It expands out into this very horrible linear combination. So this will end up looking something like, 1/2, what's it, 0.4 x1, this super horrible linear combination minus mu squared. You can expand this, but this is the equivalent, because x1 to x7 are all, we're considering them all as variables right now, right? Same with mu. This is the equivalent of doing because we've done a minus b squared before, that's pretty easy. This is the equivalent of doing a minus b minus c minus d, so forth squared. You can work this out.
Yeah, what I'm saying is, after that, you write 0.2 times x1 minus mu in the bracket. And
Zero.
plus, the next factor is 0.1 times x2 minus mu in the bracket again. And add all those, and then, I want the mu.
Unfortunately, the mu is within the square, so you only get one mu to distribute among all 7. Yeah.
But then we have the independence of x1, x2, x7.
I can't quite see what you're trying to go here. I don't think that works, though. Because you're trying to, the only way we can get the independence here is, the independence only works if we're multiplying the x1, x2s. So splitting them up doesn't really make any difference because they're not, you don't ever have a case where you have x1 times x2. Oh, if you expand it out, you do, but you don't. It's a way more complicated way of doing this, I think, because you'll end up having to deal with probably 8 different separate calculations. I think the easiest one is just to directly plug it in. So if you directly plug it in, you end up with variance of 1/2 0.4 x1 plus 0.1 x2 plus ... plus 0.2 x7. And then kind of I think it's not linearity, but you can distribute the variance through. First things first, that 1/2 comes out, becomes 1/2 squared. So 1/2 squared, variance of 0.4 x1, so on. And then you can distribute variance inside and square each of the coefficients. And you end up with, I'm going to change this into 1/4. 1/4 of 0.4 squared variance of x1 plus 0.1 squared variance of x2 plus all the way up 0.2 squared variance of x7. And then in a similar way as to how we kind of did this, where we know that the variance of each element is known to just be sigma. I'll write this back. In fact, I believe, have we given this? With unknown and known standard deviation. So yeah, this is known, right? So we know that the variance for all xi is equal to sigma squared for all I equals 1 to 7. And so for these, we can replace all of these with sigma squared. And then it just becomes a matter of taking all your 7 coefficients and then squaring them. Another way, you can distribute that 1/2 into all your coefficients, so you don't have to multiply by 1/2 or 1/4 later. But either way, if you work this out on your calculator, I believe you get something along the lines of 1/4 times 0.8555 sigma squared, which works out to 0.21375 sigma squared. And then for T2, once again, T2 being nice and friendly, the variance of T2 is equal to the variance of x1, which is equal to sigma squared. And then I showed earlier that because all of our estimators are unbiased, we have that the MSE of Ti is in fact equal to the variance of Ti for I equals 1 to 2. And so these are actually the mean squared errors. And now it becomes immediately apparent. The mean squared error of sigma of T1 is 0.2 sigma squared, whereas the mean squared error of T2 is sigma squared. So even though both of these we showed are unbiased, T1 actually has almost 5 times less mean squared error than T2. And so this is the intuition for why we would prefer T1, which you guys are all correct about. And then if you're curious as to where this shows up, it's kind of mirroring the central limit theorem, where the higher your n goes, the more n's we consider, the closer we get to the true value. This is the same. We're considering 7 more elements than T2. And so we would expect that something to improve. And here, the improvement is the mean squared error. Any questions regarding that? No? OK. And then final one. This one's pretty quick. I'm just going to go over this one right away. What are the sampling distributions of T1 and T2? So we know that xi follows normal distribution with some mu and some sigma squared for all I equals 1 to 7. And then what property are we using for here? We're using the concept that any linear combination of normal random variables is also normal. So we know that T1 and T2 are normal. All that remains is to calculate the mu and sigma, but it just so happens we did those in part A and B. They're both unbiased, so we know that T1 and T2 follow some normal distribution. They're unbiased, so their mu is 0. And then their mean squared error, again, because they're unbiased, it's just a variance. We just happen to find the variance here. And so the variance we always calculated, 0.21375 sigma squared and sigma squared. And you can leave your answer like this because we know that mu is unknown, but standard deviation sigma is known. So even though I haven't given you what sigma is here, this is a totally valid answer because these are all observed values. Yes?
Aren't the mean is the same as mu for both T1 and T2 because expectation of T1 and expectation of T2
Yes.
instead of 0?
The expectation, oh, excuse me, yes, they are mu, not 0. Mu and mu. There you go. Yes, thank you. So yes, mu, and then the sigmas we have given. Yep, so that just means that in terms, if you want to imagine what these would graphically look like, the sort of histograms for xi, T1, and T2, all of xi, slightly longer line, follows maybe this kind of normal distribution, right? If this is xi, then it turns out that ti, or T2, sorry, follows basically the same distribution. And then because the variance of T1 is smaller, they are centered at the same value, but its variance is just a little bit smaller. And so this is what T1 might look like. All right, on to the next question. Yes, for which one? Yeah. Yep. Let me zoom out a little bit more for you. All right. There you go. Good. Okay. On to question 3. Let x1 to xn be a sample of size n from some normal distribution where our standard deviation, or sorry, our variance is known. To save you some work, this is 15 squared. And mu greater than 0 is unknown. Find the likelihood function for the normal distribution. Yes. Oh, you have it? As far as I see, you have the PDF of it. Do you have the likelihood function for it? I don't see it on your. This is the cheat sheet you guys have. Do you guys have it on your cheat sheet? The likelihood function for normal? I don't see it. I don't see it on here. Yeah. So I'll give 3 minutes anyway. You have the function for likelihood, which is, I believe, something like, for all of our n, the product n equals 1 of fx xi. So that's your function for likelihood. So yeah, 3 minutes on the clock. You don't have to find the MLE, but yeah, just give me the likelihood function. Let me see what you guys have. Likelihood, Fisher, built-in factorization theorem. Sorry, I'm going to check the battery on this. Okay. About a minute left. That's roughly enough time. So I'll start working this out. As stated above, the likelihood function, this is the wrong pen. The likelihood function is the sum of all their individual PDFs. You are given on your cheat sheet the PDF for the normal distribution. So we know that this is equal to the sum from I equals 1 to n of, sorry, yes, product. The product from I equals 1 to n of 2 pi sigma squared, the power of negative 1/2, times e to the power of negative 1/2, or 1/2 sigma squared, xi minus mu, I believe this is squared, yes. We expand this out. So when you're multiplying exponents, you're adding up, when you're multiplying things with exponents, you're adding all of these up. So this becomes 2 pi sigma squared negative n/2. And then the exponential of negative 1/2 sigma squared. And then because we don't know what the xi's are, we can't add them up neatly. So it's the sum from I equals 1 to n of xi minus mu squared. We have our sigma squared here. So I'm going to go ahead and plug this in. This becomes 450 pi minus n squared, expectation, negative 1/450 sum xi minus mu squared. All right. Now then, we have our likelihood function. On to part B. Actually, does anyone have questions about part A? Does this make sense to everyone? All right. This might be one you've done in class, but it's good to redo again here. So, for part B, suppose I went and generated these 5 values. I took some previous exam distributions and I considered them as normal, and I generated some 5 values for you. And they are as follows: 75, 67, 54, 84, and 52. Assuming that these scores follow normal distribution so that we can use the likelihood function we did in part A, I want you to calculate the maximum likelihood estimate for the average score. And of course, average score here is mu. Did you guys go over what the MLE for sample mean is? If not, you will have to use your likelihood function to do it. If you're curious, by the way, the MLE for mu, I'll write it here. The MLE for mu, which we'll call mu hat, is equal to the max, the argmax mu of the likelihood function we just calculated. Which is equal to the mu where the first derivative of this equals 0. There you go. So this one I'll probably give 4 minutes. 4 minutes on the clock. This one? Oh, it's the value of mu where the first derivative of your likelihood function is equal to 0. It's also worth mentioning, I believe you have log likelihood here. It's really hard to differentiate the likelihood function I would highly recommend you differentiate the log likelihood function instead. Yeah. Because for logarithms will preserve locations of extremums. So there you go. Oh, I'm almost out of time. There's 2 hours in this, but I do have to give time for Malhar. So I'm actually just going to keep working now. If you're still working, go ahead. But I'm going to start working on the answer. So firstly, to calculate the MLE, I'm going to do exactly what I showed up here. I'm going to take the log likelihood. And so the log likelihood of our likelihood function is as follows. I believe it's something along the lines of log 450 pi minus n over 2. And then logarithms product becomes addition, so this becomes plus. If you take the log of an exponential, right, it's log to the log of e to the power something, it just removes it entirely. So it instead just becomes minus 1, 450, sum n I equals 1 to n xi minus mu squared. Now then, the first thing we want to notice is, well, the first thing I want to do is take the first differentiation of that. So this is a constant with respect to this, so this just disappears. This gets preserved, and so this becomes the sum of 2xi minus mu. The negative goes out, so this becomes plus. I believe it looks something like this. So, and then when we're maximizing functions, or when we're finding out where they equal to 0, we don't have to think about constants anywhere. We don't have to think about this. This equals 0 if if sum from n I equals 1, xi minus mu equals 0. That means that we technically have, if we expand all of these out, we have sum from n I equals 1 xi minus n mu equals 0, sum xi equals n mu. And then we arrive back at the same formula that you've studied before. So this is how you calculate that the MLE is actually this like sample mean. And then knowing this, all we have to do is plug in our numbers, and I believe this is equal to something like 66.4. Let's see. I had to do this in R earlier. Yes. Now then, this one is more of a theoretical question. I want you guys to think about why the normality assumption that I gave in part B, where I said, assume I took these scores from some normal distribution, why it's not really sensible. So if you have, this is more of a discussion than anything else, so I'm not going to give time for this, but If you guys think you have a reason as to why it was wrong of me to make this normal assumption, feel free to raise your hand. If not, I'll go over it. Yes?
Might be skewed to the right or to the left, depending on the class and direction and everything.
Maybe? Yes?
It's almost certainly not a normal distribution. Normal distributions are unbounded on both sides, and our scores are bounded by 0 and 100.
Yeah, and I believe you had one as well? No? Okay. You're both right. For one, yes, it might be very skewed. You would assume, no, the better your professor is, you might see a more rightward skew, worse your professor is, more leftward skew. But you kind of hit the nail on the head here. The normal distribution, the support of the normal distribution is every real number, right? It's from negative infinity to infinity. But inherently, our scores, and it's very clear from here that our scores are from 0 to 100. So even chi-squared might have been better here, but just the support does not line up. The support of the normal distribution equals the entire real number line, but scores are elements from 0 to 100. All right, one final question. I'll probably give 3 minutes for this, and then we'll take a break. Yes? Oh, yes, sorry. If you want a picture of it, here is all of question 2. All right, last one before we take a break, question 4. Let x1 to xn be an n-sized sample from the normal distribution. And I'm going to give you some arbitrary parameter here, which is the expectation of x minus mu cubed. So not sample, not variance, which is squared, but cubed. I want you to find the method of moments estimator for this psi. And yeah, just find the method of moments estimator. There will reach a point where you probably have to do a lot of work to simplify it. You don't have to do that for now. Just get to a point where they're all in that sort of method of moments form. And then it is helpful, there's a typo here. I thought I fixed this, but I didn't. It is helpful to know that this is the formula for cubics. There you go. So yeah, I'll give 3 minutes. I'll go over the answer, and then we will take a short break. Mm-hmm.
You said I could add something to this question. What was it?
Are they rejecting or?
Failed to reject.
Then ask, without calculating the actual p-value, whether or not the test at 90% confidence or at 95% confidence would reject.
It may or may not. But
95%? The confidence would just be wider, so it would always contain it. If the 90% contains it,
Right,
then the
right,
95%.
right.
Yeah. I'll do 1 minute left. Okay, I think that's close enough. For those of you who are actually curious, by the way, this psi here, if you divide by, I'm on erase again, if you divide by sigma cube, then it equals something called skewness, which is something you might run into in like your future stats courses. However, introducing the sigma cube is a huge pain in the ass for a method of moments, so I will not do that. But yeah, I will work this out. We will just sub in. So the method of moments estimator here, we know that, well, for one thing, method of moments estimator, the expectation of x to the power of k is equal to, or not expectation, excuse me. Oh, no, it is, yeah. An estimator for expectation of x to the power of k is 1 over n times the sum from n from I equals, or from I equals 1 to n of xi to the power of k. Am I doing that right? Yes. Okay, so let's do this. We know that the expected value of x minus mu cubed expanded out is equal to the expected value of x cubed minus 3x squared mu plus 3x mu squared minus mu cubed, all on that big old expectation. First things first, we now have some odd semblance of a linear combination. So let's distribute our expectation. So that equals the expectation of x cubed minus 3 times, again here mu is a constant, so 3 times mu, the expectation of x squared, plus 3 times mu squared, the expectation of x, minus expectation of mu cubed. Mu here is a constant. The expectation for any constant is just the constant itself. So this is just mu squared, or mu cubed. Now then, we can start to work these out. First things first, we realize that expectation of x, we are given that's mu. So this is just mu. And then this is equal to expectation x cubed minus 3 mu expectation x squared plus 3 mu cubed minus mu cubed. Please tell me I did this right. Yes. Which then simplifies just to 2 mu cubed. From here, we now have x in the form of this, so we can estimate it. So therefore, an estimator of this is equal to 1 over n, sum from I equals 1 to n of x cubed minus 3 mu times, or you know what, with mu, I'm going to also use the method of moments estimator. So 3 times 1 over n. Oh yeah, probably note mu here equals expectation of x. Equals 1 n xi multiplied by the 1 over n goes through, so this becomes squared. N I equals 1 xi squared plus 2 over mu of I equals 1 to n xi cubed. And we can stop here because simplifying this is a huge pain. But this is your method of moments estimator for psi. I'm going to leave this up here while we take a break.
I think the last
You're missing a 3.
I am missing a 3. Thank you. I'll change that n squared as well so it's neater. 3 over n squared. There we go.
the last expression. I think it's 2
Ah, yes. Thank you. Yeah. Yes. That right? Yeah. All right. I will leave this here for those of you who want to take a picture of it, but we will now go to a break. And after that, Malhar will take over.
There's no one that's left behind in the bathroom. But my component of this review seminar, excuse me if I could get your attention, please. Excuse me. We're going to get started. My part of this review seminar deals with confidence intervals and hypothesis testing. What you'll see in your exam is usually a simple question. They're going to ask you two-sided 95% confidence interval, maybe one-sided. Very rarely they might ask you for a confidence interval for the variance. But I've tried to create a few questions based off of your lecture material and the textbook. Hopefully they should be reflective of what you'll see on the midterm. I'll give you guys a minute to read question 5. Well, actually not a minute, maybe 30 seconds to read question 5. One thing to keep in mind, I've written down a few values that you might need to use, either in question 5 or question 6. Okay? I don't think you'll need to use all of them, but the ones that you will need to use are over here. Oh, yeah, that's a typo. It should be 10 students. Let's correct that immediately. Okay, hopefully everyone has read the question. Please try and do part A, a two-sided 0.95 confidence interval for the unknown parameter, the mean. Where's the value for what? That's on your cheat sheet, right? Carry your cheat sheet. But 0.975 is a very common value. Who can tell me 0.975? Yes. 1.96. Memorize it. Has anyone computed the mean for this? Yes, 62. Okay, do we have everything we need to compute the confidence interval now? Yes? What's the formula? Yes.
X bar plus minus sigma over the square root of times x. The value is 1 plus gamma.
Right. Okay. 62 plus minus, and I think this is approximately 1.368. Or sorry, 386. So if you were to compute the confidence interval, you'd get something like this. Right? And that's it. That's all you have to do for this question. Okay. Any questions? No? We'll be moving on to part B. Part B is similar, except instead of a 0.95 confidence interval, we want a 0.9 confidence interval. And instead of a two-sided confidence interval, we want a left-sided or a lower confidence interval. What's the only thing that changed? Yes.
The only thing that changes
In terms of the computation.
in terms of computation is that the left bound is negative infinity.
Okay,
And
and?
the right bound, you replace the z value with z 0.9.
Yes. We have to use z 0.9 instead of z 0.975. So the confidence interval, because it's a lower confidence interval, the left side is minus infinity. The right side would be 62 plus z 0.9, which I've said is 1.28, and the square root. Okay. And if you were to compute this, this is approximately 0.905. So your left-sided 0.9 confidence interval would go from minus infinity to 62.905. Okay? Questions? No questions? Pretty straightforward, right? It's just using the formulas that have been given to you in class. The trickiest part is to understand which one to apply, okay? Once you're confident that you can pick the right formula to apply, the application is fine. Yes? A left-sided confidence interval is a region in the support of the distribution such that starts at the leftmost possible value. So for the normal distribution, it starts at minus infinity. We want just the right endpoint such that the entire area under the PDF up until that particular point is 0.9. Yes, everything to the left of sort of. And for us, it gives us 62.905. Right? Okay. Let's move on to part C. We now have to assess this particular null hypothesis, that the mean is 60. Just looking at the, let's say the two-sided confidence interval, do we think that we will reject it or fail to reject it? Yes.
It looks like we're going to fail to reject it. Knowing that 32, that we're going to reject it because it's outside.
Right. Looking at this 95% confidence interval, since 60 is outside this interval, it seems like our hypothesis test will likely tell us that we will have to reject it, right? But we still have to compute it. Here's a value. You might have to use some value from here. But the tricky part is to identify how we're computing the p-value. Can someone tell me what the formula is? Yes.
2 times 1 minus this up until infinity values x bar minus 0 over standard deviation divided by square root of it.
Correct. Well, let's not forget the absolute sign, but yeah. So this is the z-test. Z-test for p-value. Do we have the mean? Yes. Do we have the standard deviation? We have n. We have mu naught. We have everything. Compute this. I'll give you guys maybe a minute or two. Actually, we're at the current pace, we're going to finish a little bit early, which is nice. Yes.
Those values going forward.
Mm-hmm.
I guess the one that you just wrote there, that's like the probability that something's less than that.
Yes, this is the CDF. Okay, has anyone computed this internal value? Yes. Yep. Based off of this, which one will we be using? The third one, right? One minus 0.9976, which is 2 times, yeah, it's approximately 0.005. Okay, so this is the p-value. Given this p-value, would we reject or would we fail to reject? P-value less than 0.01. What do we do?
576, not 77.
It's just a value that's given for you to use.
So that's the value. If you're given the table, would you round up or down?
Wouldn't matter. We don't care about specifics. If rounding if that small rounding actually impacts you rejecting versus failing to reject, then that's not a good test at all. No, you reject. When the p-value is smaller, you reject. When the p-value is larger, you fail to reject. And this makes sense. This agrees with our 95% confidence interval. Yes?
I've noticed in the textbook sometimes when the p-value is higher, they say we fail to reject, but it's because we don't have enough information. Is that just something they add on, or is it?
The distinction between failing to reject and failing to reject due to lack of information is not significant. Any low value. It's 0.01 is a standard preset. You can also alternatively use 0.05, 0.1 as well. But in either case, this is definitely a very significant value. So you'd reject in either of them. But these are the standard values you use. If I have time at the end, I'll briefly describe what the p-value actually means, like what the interpretation is. OK. Part D and E are basically repetitions of your previous parts. But this time around, we're dropping the assumption of the variance. We don't know what the variance is. So we have to recompute. OK, let's have a quick interjection. There's a few things we need to do because there are things that we couldn't do. Well, there's things that we can't compute anymore. Number one, what do we not know now? Yes. We don't know the variance. So what do we need to compute? Sample variance. OK. Great. Now, for the confidence interval, can we use the standard normal? What distribution do we have to use? Yes.
You got to use the t distribution with the degrees of freedom of the geometry.
Yep. You need to use t 0.975 with 9 degrees of freedom instead of z 0.975 that we were using earlier. OK, we already have this value. So all we need to do is compute the sample variance, and then we should be good to proceed. Can someone compute the sample variance for me? Okay. Does anyone have the sample variance for me? Yes. 503? 5 over 3? No, that's incorrect. Yep, 8 point something. You're close, so I'll just write it out. It's 8.459. All right? Great. So now that we have this, all we have to do is actually apply. Let's find the margin of error. Right? Everyone's comfortable with the term margin of error, right? It's in the confidence interval, it's half the width, or actually it's how far you're deviating from the sample mean. So the margin of error in this case, since we're using this t-distribution quantile, would be 2.262 times, instead of sigma, now we have the sample standard deviation. Let's actually sample standard deviation, 8.459 divided by the square root of 10, which according to what my calculator says is approximately 6.05. So then if you were to compute the confidence interval, you'd get this interval over here. Compare this with the interval that we got in part A. What do we observe? Yes. It's much wider. Why? Yes, because of, instead of assuming the variance to be 5, we're actually using the sample standard variance or the sample standard deviation, which is much higher, right? And therefore, you'd expect your interval to be much wider, right? It's a quick sanity check as well, just to make sure that you're going on the right track. You would expect this interval to be wider. Okay.
Wait, can you show me how you calculated the sample variance?
Well, the sample variance, that's just the formula. That's the square root of 1 over n minus 1 times the sum of each xi minus mu, minus the sample mean squared. It should be on your cheat sheet, hopefully. And it's a very menial thing that you'll have to do, but you'll have to do it. Okay, so be quick with it. Okay. Part E, reassess this hypothesis. Okay, so now just like we couldn't use the z-quantile, we can't use the z-test for the p-value anymore. We need to use the t-test. But without even computing this, just looking at the interval we created, would we reject? Would we fail to reject? What do we think? Yes. Fail to reject because 60 is in this interval, right? Okay. But let's see. We need to compute the t-test p-value. Which is essentially identical except that instead of the CDF of the normal, you're using the CDF of the student t-distribution with n minus 1 degrees of freedom, and instead of the assumed standard deviation, you're using the sample standard deviation. Okay? You'll probably be able to find this g value over here. You want g9 because n is 10, so it's one of those three. And we need to compute this internal value first. Someone compute this quick. This is essentially what will be a big part of your exam. So you need to make sure that you're quick. You don't make mistakes when you're typing into the calculator. Most of my time in B57 was spent just doing every calculation twice to make sure I didn't make any mistakes. Okay, any calculators? Any solvers for this? What do we have, 0.7 something? Yeah. Let's say it's about 0.74767. Okay, so which of these will we be using? The first one, right? Oh. 1 minus G 9.75 is 0.7638. 0.7638. You compute this, you get 0.4724. P-value greater than 0.01 or 0.05 or 0.1 implies fail to reject the null hypothesis. Okay? And this makes sense. It agrees with the confidence interval we computed. Any questions? Yes? It is. Your cheat sheet has certain values that are necessary. And right, because this particular midterm that this sample cheat sheet was gotten from didn't have it, but when it will, you'll have something like this. Okay? Okay. Do you have a question? I can't do anything about that. That means your computation. 8.459? That's what it was. Okay, great. We get to move on to the last question. This is population proportion. What is this underlying distribution of the population? Bernoulli, correct. You can do the confidence interval directly, and then there's something tricky that you need to do for finding the p-value. Okay. How do we compute the confidence interval when it's population proportion? We don't do the sigma over square root n. We do something else. Yes.
We still take a z value and then use square root
Mm-hmm.
and x bar times 1 minus x bar
Yep. And?
over n.
Yeah.
So we use the z in this case?
Mm-hmm.
Oh, right, we do know. Sure. So we don't use t.
Given the proportion, you know the exact variance,
Okay.
right? So that's a really good question. No, nowhere in the question is the variance given. Why is it not given? Yes, go ahead. Yeah. You're given exactly the proportion. You have the exact data set. You have the exact sample. You can compute the variance. That's why you use the z. That's why you use the normal distribution instead of the t distribution. Really good. Is that the case? Oh, correct. Okay, great. Well, we know this is, wait, it's not even, okay, 0.95 is 1.6 something? 1.645. 1.645. Great. And you would just compute this. I'm not going to go ahead and compute this. This is just plug and play. Okay, on to the next part, p-value. Notice that this one doesn't say how to assess the hypothesis, but p-value is a very generic way, and the alpha is not given to us anyway. So we need to compute the p-value. How do we go about computing the p-value? We need to compute the the sample standard deviation, right? And we need to use the t-test. We can't use the normal distribution test, right? The current mean is 0.62. The hypothesis is 0.65. Ooh, 50. Okay. Computing this internal value, you'll get something like this, right? I'm sparing you the computation now. You've had enough practice for this. So which one? The third one, right? The last one, 0.975. 0.835. This gives you approximately 0.33. Okay. P-value greater than 0.01. Okay. Just one important thing over here. How are we computing the sample standard deviation? Well, given that 0.62 of the sample answered yes, that's exactly 155 people that said yes and 95 people that said no. And then so you can do 1 and 0 and actually compute the sample standard deviation. 1 over 249, and you'd get something like this. 155 times 0.38 squared plus 95 times 0.62 squared. Over 249. Okay? That was the one sort of tricky part, but that's it. Cool. So we have some time to spare. So I'd like to talk about what the p-value is. Oh, did I close it by mistake? Sorry. There you go. Here's all of question 6. What is the interpretation for the p-value? Can someone tell me? Yes.
All I know is that sometimes we're given alpha to determine a rejection region.
Yes.
P-value is like the lowest possible alpha.
After which? If you go any lower, then what?
It becomes extreme.
Yeah. Yeah, correct. I'll give you, this is from your lecture notes anyways, but this is how I interpret it. Your p-value quantifies that given the, under the assumption of the null hypothesis, what is the probability that you'll find another sample, a random sample, that is even more extreme than the current one. So what does this mean? For p equals 0.5, it just means if I were to take a random sample again, then half of the time that random sample will be even more extreme than what I have right now. Okay, that means this is around the ballpark, the current sample, and is representative of the actual population. But if my p-value is 0.0001, this means that out of 10,000 other random samples, only one will be more extreme than what I currently have. More extreme. That's a good question. More extreme in the sense that the parameter for the sample is farther away or more deviated than the parameter that is in the null hypothesis. Yeah. Just the distance between them will be larger. Okay, that's it for this review seminar. Thank you so much for coming. Good luck for your exams, and if you're in some other courses, look out for those review seminars too. Sure.